Welcome to Taskology, utilizing task relations at scale. Computer vision tasks are interrelated. That's because different tasks represent different forms of understanding of the same visual world and oftentimes even the same scene. It's been shown that the relations between tasks can be revealed through training them on a large body of labeled data. In this paper, we wish to take the opposite route. What if we know the relations between tasks through the geometry and physics that constrain a visual world, or through any other means? Can we then reduce the reliance on labeled data and utilize the relations to improve the performance of various tasks? Our answer is obviously that yes, and we're going to present a general and scalable method to do exactly that. Let's start with an example where we have three tasks: depth estimation from a single image, dense 3D motion estimation from 2 consecutive frames, and segmentation. Projective geometry ties these tasks closely together, right? Knowing to segment moving objects helps regularizing the motion field, as it can be used to partition it to background motion plus the object motion. In turn, dense depth and motion maps induce an optical flow, which can be used to track objects, and ascertain that an object properly segmented in one frame will also be properly segmented in the next one. The relations in this particular example can be expressed as a set of differentiable consistency constraints through which we can push gradients. Think of a loss like the one here. Each task may receive supervision from a small labeled dataset, and in addition, the tasks supervise each other through the consistency constraint. The latter can be imposed using a very large unlabeled dataset, which we refer to as the mediator dataset. The diagram above shows how it would work for 2 tasks, but it would work in the same way for n tasks. So this is a multitask learning setup, but unlike the other approaches, we keep the models completely separate and let them interact through their predictions only by the consistency constraints. In fact, our framework trains each model on its own separate machine with its own set of hyperparameters as published by the model's author. Each model is a black box in the best tradition of deep networks, and the framework is completely agnostic to how a model performs its task, as long as it can output predictions and receive gradients. This is a modular design that opens the way to scaling multitask learning, just like modular software design enables creating software at scale. So let's go back to the trio of tasks introduced earlier. If we train a depth and motion model separately from the segmentation model, they all achieve certain test metrics as shown here. Now let's tie all 3 tasks together. If we let gradients flow from the segmentation model to the depth and motion models, the depth metric improves. Let the gradients flow to the segmentation model, and its metric will improve too. The best results are obtained when the gradients flow both ways, or in other words, when all models supervise each other. In this experiment, Coco was used as a label dataset, and Cityscapes, with the labels stripped off, was used as a mediator dataset. In another experiment, we jointly trained object detection and object tracking in point clouds. You can imagine that if one task outputs a bounding box for each object, whereas the other one estimates the change in position and orientation of an object given 2 consecutive frames, it's easy to tie them together via a simple differentiable consistency constraint. The experiment here was performed on the Waymo open dataset, where a small part of it was used with its labels for direct supervision, whereas the rest was used with the labels stripped off as a mediator dataset for imposing the constraint. You can see that switching on peer supervision improves the metrics on each task separately. Moreover, the less labels we use for supervision, the more dramatic an improvement we observe. Consistency constraints are especially valuable in the underlabeled regime, and in real life, we're kind of always in that regime. Last but not least, since the models communicate through predictions only, the communication load is very small compared to other parallelism schemes. We found that the task-level parallelism we introduce is extremely robust against asynchronicity and staleness. Each model can see 20 minutes old versions of its peers without any loss of accuracy. To conclude, we introduced a multitask learning method where known relations between tasks are utilized to improve their performance using unlabeled data. Our method is general, robust, distributed, asynchronous, scalable, and agnostic to the implementation of the constituent tasks. Each task lives in its own universe of hardware and hyperparameters, making it easy to incorporate published models. An exciting future direction is to see whether learned differentiable relations can be utilized in a similar way.